Hello, it's David Shreeve, Algebra 2 instructor with Florida Virtual School. Today we're going to be looking at solving a system of three equations with three variables. Basically, we're going to do a lot of work to get this down to a system of two equations with two variables. So we need, as a prerequisite skill set, all of the work back from the prior lessons in the unit, such as substitution, elimination, solving systems, all of that. All right, so first thing I like to do is keep all of these very organized. So I'm going to just kind of label my equations here: equation 1, equation 2, equation 3. And I usually try to start looking at just these top two, see if there's something I can use, either substitution or elimination. I'm going to be using elimination in my examples here, but just a big part of the efficiency as far as the work is concerned is what I'm going to do to analyze these from the start. When I look at the coefficients on my x variables here on equations 1 and 2, I would have to, for elimination anyway, I would have to multiply both equations by a variable, or by a number rather. I'm trying to cut down on the number of calculations I do so I can increase my accuracy. Here I could multiply this bottom one by -3, so that might be a good option. Up here I can multiply the top one by a +2. That would eliminate my z variables. So that looks to be the best option here. So I'm going to multiply this top equation by a +2. Remember, there are several correct ways that we could go through this. This is just what I'm choosing to do based on analyzing the system. So go ahead and multiply the top equation 1 by +2. That's going to give me 4x plus 6y minus 2z equals 2. And then I'm going to rewrite equation 2 right under it here. That's 3x plus y plus 2z equals 12. I'm just going to add them together here. 3x plus 4x here is 7x plus 7y equals 12 plus 2 is 14. Because -2z plus 2z, of course, is 0. So all I did there was eliminate the z variable. Now I've got a regular equation with just an x and a y variable. Now, what I'm going to do next is, I already eliminated the z with 1 and 2. Now I'm going to eliminate the z with equation 3 and one of the other equations. It really doesn't matter which one. It looks like it would probably be easier to eliminate the z using equation 1 and 3. In other words, I would only have to multiply this top equation by a -3 to eliminate the z. If I use equation 2 and equation 3, I'm going to have to multiply the top by 3 and the bottom by 2. So again, from an efficiency standpoint, I want to do as few calculations as possible. So let's go ahead and multiply the top by -3. So this is equation 1. I'm distributing a -3 through all the terms here. It gives me -6x minus 9y plus 3z equals -3. Now I'm going to rewrite equation 3 right here so I can add these together. And you'll notice the z's here are going to cancel. So -6x plus x is -5x. -9y plus 2y is -7y. This again is 0. -3 plus -5 is -8. So now what I'm looking at is I've got two equations with only two variables. And this isn't always going to happen, but just looking at what I have now, if I add them together, it's going to eliminate my y variable. So that just happened to occur. That's usually not going to be the case. Usually we'll have to go through that elimination process or substitution with these again. By the way, Substitution would be easy to use here since all of your coefficients are divisible by 7. If you do prefer to use substitution, that's one way you could do it. So I'm going to rewrite my two equations that just have the two variables over here. And I'm not going to use substitution basically because what I'm looking at is this. I've already got opposite coefficients on my y variable there, so this is going to make solving for x very easy. 7x plus negative 5x is going to give me 2x. These will be 0 because it's 7y plus a negative 7y. And 14 plus a negative 8 is the same as 14 minus 8, which is 6. And then from here, we're just solving a regular linear equation. So divide each side by 2. X is equal to 3. Now I've got one variable to solve for, but I've still got a ways to go because I still need to solve for my x and for my y. Now, I'm just going to use these equations to find out what my y value is. Then we'll plug our x and our y back into any one of these equations. I'll probably just plug it into the top equation there. So x is 3. I'm going to plug that in. Let's do this top equation here. 7 times 3, which is 21, plus 7y equals 14. 21 plus 7y equals 14. Subtract the 21 from each side. 7y equals negative 7. Divide each side by 7, and y is negative 1. So now I've got 2 of my variables solved for. And I'm just going to plug my x and y value in. Doesn't matter which equation. I can plug it into any equation. I'm just going to use the first equation there. So 2 times 3 is my x value, plus 3 times negative 1 is my y value, minus z equals 1. And just to kind of have some separation here from the other work, I'm just going to box this. Okay, so 6, this would be plus 3 times negative 1, which is plus a negative 3, which is just minus 3, minus z equals 1. 6 minus 3 is 3. And then subtract the 3 from each side. Negative z equals negative 2. And here you can multiply each side by negative 1, divide each side by negative 1. But the point is we want to solve for z, not for negative z. So there is an assumed coefficient of negative 1 there. I'm just going to divide each side by negative 1. That's going to give me z equals 2. So there are my 3 solutions, and sometimes you'll see them written this way. 3, comma, negative 1, comma 2, like that. All right, I hope this was helpful. Let's see, make sure you can see that. Good. All right, guys, good luck on these systems of 3 equations with 3 variables.